Hello everyone, this is Hussam Safieh and I will be presenting our topic titled Prediction of the Compressive Strength of Normal Weight Concrete with Variable Fly Ash Percentages Using Machine Learning. The authors of this paper are myself, Dr. Rami Hawileh, Dr. Sayan and Dr. Jamal Abdalla. In this presentation, we will begin with an introduction to our topic, followed by a discussion of the research objectives. We will then move on into the data collection process, followed by an analysis of the data. After that, I'll present the results from our machine learning models. Finally, we will wrap up with some concluding remarks. Let me begin by discussing the importance of compressive strength in concrete. Compressive strength is a critical property that directly impacts the structural integrity of buildings and other infrastructure. It's the measure of how well concrete can withstand loads without failing. Now let's talk about fly ash. Fly ash is often used as a partial replacement for cement concrete. This substitution not only helps in reducing the environmental footprint of concrete production, but also can enhance certain properties of concrete, like workability and long-term durability. Finally, I want to emphasize why predicting the compressive strength is so important. Accurate predictions allow us to optimize mix designs, ensuring that we achieve the desired strength and performance characteristics efficiently. This is particularly valuable in construction projects where quality and reliability are paramount. Fly ash is an important supplementary cementitious material that results from coal combustion. It's increasingly used in concrete mixes due to its beneficial properties. Typically, fly ash is used to replace about 10 to 30% of the cement content in concrete. This substitution not only helps in reducing the amount of cement needed, which is more sustainable, but also can enhance certain characteristics of the concrete. The impact of fly ash on concrete strength varies for the percentage used. Lower percentages of fly ash generally contribute to better early strength development, which is important for projects requiring quick strength gain. On the other hand, higher percentages of fly ash tend to enhance the long-term performance of the concrete, making it more durable and resistant to chemical attacks. Concrete compressive strength is crucial because it directly impacts the material's ability to bear loads, making it a primary consideration in structural design. Fly ash plays a significant role by contributing to the pozzolanic reactions. These reactions not only enhance the concrete strength over time, but also improve its overall durability. Lastly, we will discuss how traditional methods of testing compressive strength compared to newer approaches using machine learning, which can offer more accurate and efficient predictions. Moving on, our study has four main objectives. First, we aim to develop a machine learning model that can accurately predict the compressive strength of concrete. This is crucial for optimizing material use and ensuring structural integrity. Second, we will analyze how varying percentage of fly ash influence the strength of concrete. Understanding this impact can lead to more sustainable and efficient mix designs. Third, we will compare the performance of the different machine learning models to identify which ones offer the best accuracy and reliability for our predictions. Finally, we will assess the practical application of these models in real-world scenarios, ensuring that our findings can directly be applied to and improve construction project practices. Our dataset comprises 680 data points collected from over 10 studies, providing a robust foundation for our analysis. The key features of this dataset include the percentage of fly ash used, the amount of superplasticizer, the water-to-binder ratio, the curing period, and the resulting compressive strength in megapascals. The dataset was collected from a variety of resources to ensure a comprehensive coverage of different study parameters and conditions. This extensive dataset allows us to explore a wide range of variables and their impact on concrete strength. Our exploratory data analysis started with the count loss to explore the frequency distribution of our key features. For instance, the distribution of fly-ash percentages shows that most data points cluster around 10 to 20%, with fewer data points at higher percentage. Similarly, the superplasticizer distribution is highly skewed, with most values concentrated near zero, indicating minimal usage in many samples. Next, we used correlation matrix, which reveals the relationship between the different features in our dataset. From the matrix, we can see that the curing period has the strongest positive correlation with the compressive strength, with a coefficient of 0.54, indicating that longer curing periods tend to increase the compressive strength. On the other hand, the water to binder ratio has a weaker negative correlation of negative 0.21, suggesting that higher water content may reduce strength. Building our machine learning model, we followed a structured approach to ensure both accuracy and generalizability. First, we split our dataset into two parts, 80% for training and 20% for testing. This 80-20 split is a common practice that allows us to train our model on the majority of the data while keeping a separate subset for evaluation, ensuring that our model's performance is assessed on unseen data. Next, during the training process, we applied several techniques to optimize our model. Normalization was used to scale the features so that they have a consistent range, which is crucial for models sensitive to the scale of input data. We performed cross-validation to reduce overfitting and ensure that our model performs well across different subsets of the training data. Hyperparameter tuning was conducted to fine-tune the model parameters and identify the best configuration for optimal performance. Finally, to evaluate our model, we use several key metrics. MSE and MAE give us insights into the average error magnitude. RMSE helps us understand the error in the same unit as the target variable, which in our case is compressive strength. R squared indicates how well our model explains the variance in the target variable. These steps and metrics ensure that the model is both accurate and robust, making it reliable for predicting compressive strength in concrete. Let's start by looking at the results from the linear. Let's start by looking at the results from the linear regression model. In this scatter plot, we are comparing the predicted compressive strength values to the actual values. The R-squared value for this model is approximately 0.297, which indicates that the model explains about 29.7% of the variance in the data. This is just one of the performance metrics we've calculated, and we'll be using R-squared as an example throughout these slides. Now, let's see how a different model, the support vector machine, performs in terms of R-squared and other metrics. Here are the results of the linear support vector machine model. The scatter plot again shows the predicted versus actual values. The R-squared value for this model is around 0.267, meaning it explains about 26.7% of the variance in the data. This slightly lower R-squared compared to linear regression suggests that SVM may not capture the underlying patterns as effectively in this case, though it has other strengths in different contexts. Next, let's explore the performance of the random forest model, which is known for its robustness and often yielding high R-squared values. The random forest model demonstrates a strong performance here. A scatter plot shows a much closer alignment between the predicted and actual values with an R-squared value of approximately 0.789. This indicates that the random forest model explains about 78.9% of the variance in compressive strength, making it the most effective model we've tested so far. Again, we are focusing on R-squared here as an example, but all of our performance metrics support this conclusion. To get a broader perspective, let's compare the R-squared scores and other metrics across all the models we've tested. This bar chart provides a visual comparison of the R squared scores across all the models we've tested. As we can see, the random forest model stands out with an R squared value of approximately 0.789, significantly outperforming the others. The support vector machine and linear regression models have lower R squared values of around 0.267 and 0.297 respectively. While we are showing R squared as an example here, it's important to note that this metric gives us a quick sense of how well each model explains the variance in compressive strength. For a more detailed look, let's examine the complete set of performance metrics, including MSE, MAE, and RMSE, alongside the R squared for each model. This table summarizes the performance metrics for each model, providing a comprehensive comparison. In addition to R squared, which we've highlighted on the previous slides, the table includes MSE, MAE, and RMSE. These metrics give us a better understanding of how each model performed. For instance, while random forest has the highest R squared, it also shows lower MSE and RMSE values compared to other models, indicating overall superior performance. This detailed comparison confirms that the random forest model is the most accurate and reliable for predicting compressive strength in our dataset. Having compared all the models in detail, we can confidently conclude that random forest is our best performing model. Let's move on to discuss how these findings can be applied in real world scenarios and the implications for future research. In conclusion, the random forest model emerged as the most accurate with an R squared value of approximately 0.789. This model was particularly effective in demonstrating the positive impact of fly ash on concrete compressive strength, highlighting its potential as a key factor in mix design optimization. But beyond accuracy, one of the most significant advantages of using machine learning in this context is its contribution to sustainability and efficiency. A well-trained machine learning model backed by a comprehensive dataset can predict the compressive strength of various concrete mixes without the need for extensive physical testing. This not only saves time but also conserves resources by making the process more sustainable. Looking forward, there are more opportunities to expand our dataset and explore even more advanced machine learning models. By doing so, it can be further refine these predictions and continue to enhance the sustainability of concrete design and construction practice. Ultimately, the study lays the groundwork for leveraging machine learning to create more durable, cost effective, and environmentally friendly concrete structures.
Thank you so much. Please let me know if you have any questions.